All right, hello everybody. Welcome back in. Hope you're having a wonderful day today. Without further ado, we're going to go ahead and get started into the stream. We're going to be watching Hands-on Deep Learning Lecture 2. This is going to be from MIT, 15773 Spring 2024. I'm recording this, so if you guys would like to check out the condensed version recording, I'll upload that later. But anyways, let's go ahead and get started with Lecture 2 here. Appreciate you guys being here.
Okay, so let's get going. Today we're going to talk about how do you actually train a neural network, right? Because that is sort of the heart of the game here. So just to recap, we looked last class at what it takes to design a neural network, and we made this very important distinction between the things that you're handed by your problem and the things that you have agency over, that you have control over. And we noticed that, the input layer for your problem, the input is the input. The output is the output. You got to do something with the output, something that's expected. But everything that happens in the middle is actually in your hands. And in particular, we noticed that we have to decide how many hidden layers we want. We have to decide in each layer how many neurons to have. And then we had to decide what activation to use, even though I'm kind of cheating when I say that, because I told you very clearly on Monday that for the hidden layer activations, just go with the relevant activation function. You don't have to think deep thoughts about this, okay? But the other things are all choices you have to make, and we will talk a bit later about how do you actually make those choices, okay? Now, the rule of thumb, right? The rule of thumb always is to start with the simplest network you can think of, and if it gets the job done, stop working on it. If it's not good enough, make it slightly more complicated, okay? So that's sort of the, like the meta thing you have to remember always when you're designing these things.
What's going on, Kamau?
Okay. So that's sort of what it takes to design a deep neural network. So what we will do in this class is we'll actually take a real example with real data, and then we'll think through how we will design a network to solve this problem.
Okay.
And while doing so, we will cover a whole bunch of conceptual foundations, such as optimization, loss functions, gradient descent, and all that good stuff.
Great.
Okay. All right. So the case study or the scenario here is we have a data.
So predicting heart disease. So we have a case study. What's going on, everybody? Welcome in. We're doing MIT 15773 hands-on deep learning. Appreciate you guys being here and hanging out with me today. Welcome in. Let me know if my screen freezes. Spam the chat if it freezes, because I don't catch it sometimes. It's been kind of buggy lately, so let me know. All right, here we go. So case study. We're going to be predicting heart disease. Using a data set of patients made available by the Cleveland Clinic, we wanted to build our first neural network model to predict if a patient has been diagnosed with heart disease from demographics and biomarkers. Great. Cool. So using a data set of patients made available by the Cleveland Clinic. We're going to build our first neural network model to predict if patients. Build our first neural network model to predict if a patient has been diagnosed with heart disease from demographics and biomarkers. Cool. All right, what we want to predict is a target of heart disease. 1 equals true, 0 is false, right? So that's what we're trying to predict for the specific patient, given a bunch of biomarkers here. So that's what we're going over here. 4 a.m. Crazy, dude. Yeah, that's crazy, the time differences. I got a lot of people from all over the places that seem to be watching the streams lately, so computer science programming is multinational, multicultural. It's all over, so it's kind of crazy. All right, let's keep going.
Data set of patients made available by the Cleveland Clinic, and essentially we have a bunch of patients,
Let
And
me
for
know if you're
all these
taking notes here
patients,
with
the
us, if you're
setting is
watching
that
along.
they have come into the Cleveland Clinic, and they have not come in with a heart problem. They have come in for something else. Maybe they just came in for a physical, and we measured a whole bunch of things about them, okay? And the kinds of things we measured are, demographic information, like what's their age, gender, whether they have any chest pain at all when they came in, blood pressure, cholesterol, sugar, so on and so forth.
Just
right? You get the
standard,
idea.
physical
Demographic
stuff.
information and a bunch of biomarker information. And then what the Cleveland Clinic did was they actually tracked these people and figured out in the next year, did they get diagnosed with heart disease or not? Okay, in the next year. Which means that maybe you can build a model when someone comes in, even though they didn't come in for a chest problem, maybe you can predict that something's going to happen to them in the next year. Right? It's a nice
this is so
sort of
cool.
classic machine learning setup.
So cool.
All right, so this is the thing. So what we want to do is we can totally solve this problem using decision trees, random forests and gradient boosting and all that good stuff you folks may have already learned from machine learning. But we will try to solve it using neural networks, okay? This is an example, of course, of what's called structured data, because this is all data sitting in the columns of a spreadsheet, right?
Yeah.
So working with structured data is the way we warm up our knowledge of neural networks. And then we will do things like working with unstructured data starting next week with images, and then later on with text, and so on and so forth. OK, any questions on this?
No, all good.
OK, yes?
Just connected even to last time's class where we took the same example, and first it was a logistic, and then we did a
Let me know
neural
how the
network.
audio
So
is, if it's too
the
loud, too
probability
quiet.
in case of one was 0.85, then was 0.22, and here as well. How do you know when to use what? Usually in textbooks, you know when to use logistic or when to use something else. But in this case, when do I complicate it to neural networks vis-a-vis, in this case, maybe just doing a random?
It's a great question.
That's a
When
good
do you use
question.
what?
Why use the
I think
neural
there are
network
two
here?
broad dimensions that you have to think about. One broad dimension is how important is it that you need to explain or interpret what's going on inside the model to perhaps a non-technical consumer. The other dimension is how important is sheer predictive accuracy. In some situations, predictive accuracy trumps everything else,
Yeah.
in which case, just go with it. In other cases, explainability becomes a big deal because if they can't understand it, they won't use it. And in those cases, it's probably better to go with simpler models, such as decision trees and decision trees, maybe even random forests, certainly logistic regression. Those are all a little more amenable. But that said, even complex black box methods like neural networks, there is a whole field called mechanistic interpretability, which seeks to try to get insight into what's going on inside these big black boxes. So the story isn't over, right? But that's just the first cut
There
way
you go, Scott.
you
We'll
sort
turn
of
it down a little
analyze the
bit.
problem. OK.
Okay, so explainability and
let's get going.
simplicity
So if you
of the
want to
model,
design a
right?
network, all right, so we design the network.
All right, so let's design our neural network, right? We design, lay out the network. We choose, let's design our neural network. So we lay out the network. Right, we lay out the network. We choose the number of hidden layers and the number of neurons in each layer. We choose the number of neurons, number of hidden layers and the number of neurons in each layer. And we pick the right output layer based on the type of the output. Okay, cool. People are so cringe with their comments sometimes. Okay, let's keep going.
So we have to choose the number of hidden layers and the number of neurons in each layer. Then we have to pick the right output layer. So here, what I did is, the simplest thing you can do is, of course, just have no hidden layer. So if you have no hidden layers, what is that model called? Yes, logistic regression. Okay? So of course, we want to do neural network, so I'm going to have one hidden layer, because that's the simplest thing I can do. And then I'll confess, I tried a few different numbers of neurons in this thing, and when I had 16 neurons, it actually did pretty well. Okay? So there was some trial and error that went on before I landed on the number 16. Right?
Okay.
And for some reason, people always use powers of 2, so may as well do that. So I tried like 4, 8, 16, and 16 was really good. And as it turns out, when I went above 16, it sort of started to do badly. And it started to do badly because of something called overfitting, which we're going to talk about later. Okay? So yeah, 16. And then by default, I use ReLUs. Okay? So 16 ReLU neurons. And then here, the output is a categorical output, right? Heart disease, yes or no, 1 or 0, classification problem, which means that we want to emit a probability at the very end. Therefore, we'll use a sigmoid. Okay? So far, so good, right?
Okay.
Any questions?
So we got to pick the right output layer. So do we want like probability, like 1 or 0? Maybe like go with like a sigmoid, like you mentioned. Right. So we would choose a layer, right? We're going to do one hidden layer with 16 ReLU neurons. There's no he didn't say any specification why he did this, right? He kind of just alluded to that you typically do powers of 2 for neuron counts. You have to have one hidden layer to become a neural network, right? At least one hidden layer. One hidden layer, right? We'll say a neural network without a hidden layer is just a linear regression model. Not really, not a neural network. Okay.
All right. So
what's going on, therapists? What's going on? Hey, Bancories, Rebel.
Okay. So we have an input, and so I just have an input, and as you will see here, x1 through x29, that's our input layer. And you may be wondering, 29, where did he get that from? Because there doesn't seem to be like 29 rows here of independent variables. So it turns out there are only 13 input variables here, but some of them are categorical. So what I ended up doing is to take each categorical variable and one-hot encode it. Okay? And when you do that, you get to 29. I'm sorry, 29. All right? And when we actually do the collab later on,
so let's make a note here. Let's make a note. Let's say things to look up. One hot encoding.
Exactly how I encoded it, but that's what I'm doing here. That's why you have 29, not 13. Okay, now, obviously, we have decided on these hidden units, 16 units, with nice ReLUs here, okay? And then we have an output layer with a little sigmoid.
Perfect.
And I got bored of trying to draw all these arrows, so I just gave up and said, assume there are arrows, okay, between all these things. Good?
Yeah.
Yeah.
Yeah, I'm sorry, I think you already mentioned this, but why 16 units?
Why 16? I tried a bunch of different numbers of units, and at 16, the resulting model did well, so I just went with that.
And the logic of why is a ReLU?
Oh, why a ReLU? Yeah, so there is just a mountain of empirical evidence that suggests that ReLU is a really good default option for using as activations and hidden layers. There is also a really great set of theoretical results, and I'll allude to some of them when we actually talk about gradient descent.
Hey, what's going on, Omar?
Yeah.
Sorry, quick question. You mentioned in the input layer, how did you get to 29 again when you had like 13 variables?
So some of those 13 variables are categorical variables, like cholesterol low, medium, high, right? And so I took them and one hot encoded them. So if it had like 5 levels, I would get 5 columns now. Yeah.
Okay, so that's it. Okay, so we don't know what one hot encoding is yet. If any of you guys do, let us know here. We're going to look it up after probably. But from what he just said there, it sounds like if a categorical variable had like, okay, low, medium, or high, you kind of have cholesterol low, cholesterol high, cholesterol medium, and then 0, 0, 1. Like, okay, yes, it is true for medium or true for high, right? So, like think of like a drop down menu or something like selected or whatever for those different categories rather than being like a solidified, just a data point, like an integer. It can have like many different options. And so by applying all of those, each of them become a category, each of them become an input, with just true marked as the one that was true for that patient. That makes sense.
And by the way, folks, just like, yeah, so just like, please use a microphone so that people on the live stream can hear your question. Yep, go ahead.
Sorry, just one question. So the vectors, since we didn't represent them, are we assuming like every x is connected to all the units?
Correct.
And this is also a parameter that we have to decide, or?
That ends up being the default. And we will see deviations from that assumption when we go to image processing and language processing and so on. But when you're working with structured data like we are doing now, that's the default. OK, so let's keep going. So this is what we have. So remember what I told you in the last class. Whenever you're working with these networks, right, get into the habit of very quickly calculating the number of parameters.
What's up, Nate?
Right? Just do it a few times, the first few times, so that you really know cold exactly what's going on.
Okay.
Okay? So yeah, how many parameters do we have here? How many weights and biases? You can work through it, okay? You don't have to tell me the final number. You can say x times y plus z, stuff like that.
Where's the photo? Okay, right. So we would have weights and biases. So let's think about this. We have bias at every at every hidden layer node, and then at the output layer node, right? So we have 16 biases, 17 biases. Oh, a piece of paper. 17 biases, and we have 29 connecting 16. So is it just we have 29 input nodes, 29 inputs. Each of them is connecting to 16 different hidden layer nodes. So it's 464 connections plus 17 biases, 481. And who's got this with me here? 481.
You don't have to tell me. Yeah.
65. You have 48 weights and
Dang.
17
Trolling.
biases.
Okay, and how did you come up with that?
So for the weights, you have, like for the first layer, it's 2 times 16. Then for the second connection, it's 1 times 16. And then the biases, the 16 hidden plus the outputs.
Okay. Any other views on this?
Oh, I don't think he agreed. Okay.
29 into 16.
Well, I think I'm way off. I got 481. Oh, dude, we're trolling. So I thought that back in lecture 1,
$29. Okay, 29 into 16.
And then 16 into 16 there.
Yeah.
And then biases, 16 biases and 1 bias.
Correct. So the way it's going to work is we have 29 things here.
Oh, we were close. What? Well, which one did we miss?
Correct. So the way it's going to work.
29. Oh, we were off by 1 row of biases. Where's the initial? Okay, we were off by 116 of biases. Right, we did the 29 into 16, 464. We added the 17 for the bias at the end and the biases in the row, but we're off by 1 by 16 here. Is it? Oh, is it because it's 1 on for the output layer, but also 16? Oh, we forgot. There's edge connections here. He didn't draw them. Remember, he didn't draw them. He said he got lazy. He got lazy. There's edge connections here. There's 16 nodes. They're all going to this one node plus 16. 497. We were so close. So close. Hey, we did better than that first guy though. He's like 65.
Is we have 29 things here, 16 in the middle, so 29 into 16 arrows. And then for each of these fellows, there is a bias
Dang, we were so close.
coming in. So that's another 16. Plus, you have 16 times 1, which is here. Plus, there is.
Let me see if I can take a screenshot of this real quick. Okay. Got you. We're kind of able to infer that, Kamau. Appreciate you on that def. Looks like we're getting one on encoding right as well.
There is one bias for this one. So the total is 497. So you can see here, there is something very interesting going on, which is that when you go from one layer to another layer, the number of weights is roughly on the order of A times B, the number of units. And so that's a dramatic explosion in the number of parameters, right? And that's something we have to watch for later on to prevent overfitting. Okay, that's where the explosion of parameters comes from, the fact that each layer is fully connected to the next layer. Okay, but we'll revisit this later on. Okay, so what I'm going to do now is I'm going to actually translate this network,
into Keras
right, the
code.
one that
Okay.
we have laid out graphically, into Keras code
Okay.
to demonstrate how easy it is. Okay, so
How do we how do you make a pie file in Markdown? Oh, I always forget. Or make like a pie snippet. Tick, 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 Python. Tick, tick, tick. Okay. Okay, cool.
I will give a fuller intro to Keras and TensorFlow later on, but for now,
What's going
just
on, VG?
suspend your disbelief. We'll just try to do it in Keras, as if we know Keras, okay? So let's try that. Later on, we'll get into all the gory details and train it in Colab and so on and so forth. Okay, all right. So the way we typically do it is that once we have a network like this, we typically start from the left and start defining each layer in Keras, one after the other. So we flow left to right, okay? So let's take the input layer. The way you define an input layer in Keras is really easy. You literally say keras.input, okay? And then you tell Keras how many nodes you have in the input coming in. In this case, it happens to be 29, so you tell it the shape. Shape equals 29. And the reason why we say shape as opposed to length is because, as you will see later on, we don't have to just send vectors in. We can send complicated things in to Keras. And those complicated objects could be matrices, it could be 3D cubes, it could be 4D tensors, and so on and so forth. So it's expecting a shape, right? What is the shape of this thing you're going to send me? In this particular case, it happens to be a nice list or a vector, so it's 29. Okay, that's it. So we write this down. This creates the input layer, right? And we give it a name, right? And the name here means this layer, whatever comes out of this layer, has the name input. Okay?
Beautiful.
Good. Next.
Next.
We specify the shape of the input, as I mentioned, right there. Then we go to the next one. And here, and we will unpack this. The way you define a layer is typically a hidden layer, keras.layers.dense, and all this stuff. Okay? So what?
Hold up. Oh, I'm streaming. Sorry, people being loud. Hold on. Sorry, guys. with 29 parameters, or okay, so 29 values are input. Okay, got you.
Basically, as I mentioned, right there. Then we go to the next one. And here, and we will unpack this. The way you define a layer is typically a hidden layer, keras.layers.dense, and all this stuff.
Yeah,
okay?
we learned about this.
So what this
in the
is,
book, right?
first of all, it says, I want a dense layer. By dense layer, I mean a layer that's going to fully connect to the prior and the later layers. Fully connect. That's what the word dense means. Okay? Number two, I want 16 nodes here in this layer. Okay? Finally, I want to use a ReLU. See how compact and parsimonious it is, right? And that is the appeal of Keras. It's very easy to get going. So the moment you do that, you've actually defined this layer. But what you have not done is you have not told this layer what input it's going to get. Because as far as this layer is concerned, it doesn't know that this other layer exists. So you need to connect them. Yes?
Do we need to define for the ReLU where the bends are? Like where you take the max?
No, the ReLU, the bend is always at 0.
Okay, thank you.
Okay.
Right, it's using a ReLU function.
So that's what we have
for
here.
activation.
And then what we do is we have to tell it, you want to feed this layer the output of the previous layer. So you feed it by taking whatever is coming out of this thing, which is called input, and you basically stick it in here. So the moment you do that, boom, it's going to receive the input from the previous layer. And because this one's output needs to go to the final layer, you need to give a name to that output. So you give it a name. I'm just calling it H because it's coming out of the hidden layer.
You
just a variable.
multiply
You
it
can call
by
anything
the
you want.
input in that layer, okay.
Now what we do, we go to the final output layer.
Just multiply it by input.
And this is what we use. The output layer is just another dense layer. That's why we use the word dense. But we say, hey, give me just one thing, because I just literally just need one unit here, because I need to emit just one probability. And the activation I want to use is a sigmoid. Done. Okay? And once you do that, you have to feed it the input from the second layer. So you stick an H here. Now you have connected the third and the second layers. And after you do that, you give a name to the output coming out of that. We'll just call it output. You can call it Y, you can call it output, you can call it whatever you want. Okay, so at this point, what we have done is...
It's kind of crazy that these like classes, that they just teach you how to use libraries, like, right? It's interesting. You would think that I get that if it's already written and it's already like there for you to use, like why, like, and kind of like the same thing applies. You're not going to college to learn how a calculator works or to do your math because you already have a calculator, right? So just learn how to do more advanced math. But like, it's kind of more of like they kind of just give you the theory behind it, and then they said, okay, now there's a theory behind it, but here's the library that already has it all, for you. So you're kind of paying like a huge tuition for the information you get out of the book, and then just how to learn a library, at least for the most part here. So it's just kind of interesting. What do you guys think about that? Like, if you have the ability to kind of read docs, it's kind of I guess, but it's harder to interpret those documents into actual application for some people. So that's why they go to classes and stuff. And that's why we're watching these classes ourselves, even though we're also reading the book too. So I think it's just interesting though that like these high-level colleges, they just kind of teach you how to use the libraries, right?
Is we have mapped that picture coming out of that, we'll just call it output. You can call it Y, you can call it output, you can call it whatever you want. Okay, so at this point, what we have done is we have mapped that picture into those 3 lines. That's it. Okay? But we aren't quite done yet. There's one little thing we have to do. So what we have to do is we have to formally define a model so that Keras can just work with this model object. It can train it, it can evaluate it, it can use it for prediction, and so on and so forth. So we tell Keras, hey, create a model for me, Keras.model, and basically where the input is this thing here, and the output is that thing there. And then the whole thing, we'll just call it model. Okay? So that's it. We are done. That is the whole model. That is, it sounds really fancy, right? A neural model for heart disease prediction. Yeah, that's pretty cool.
4 lines of code.
4 lines. And we will show how to train this model with real data and so on and so forth, and use it for prediction after we switch gears and really get into some conceptual building blocks. We had a question.
You teach us how to use raw Python?
Can you define a custom activation function that is not in the list of Keras library?
Yes. Yeah, you can define, the question was, can you define a custom activation function? You totally can. And in fact, I mean, the kind of flexibility you have here is incredible. And these innocent 4 lines, unfortunately, sort of hide the potential that's possible here. But I guarantee you,
definitely.
in 2 to 3 weeks, you folks will be thinking in building blocks like Legos. So you'll be, I'm so happy when it happens. Students will come to my office hours and say, I want to create a network where I have a little network going up on top, and one going in the bottom, then they meet in the middle, then they fork again, they split. I'm like, unbelievable. It's fantastic. And you're going to be doing this in 2 weeks, I guarantee you.
Let's go, 2
In
weeks.
the case of a multi-class classification problem, are the output nodes equal to the number of classes?
Correct. So we will come to, so this is binary classification. And the question is for multi-class classification. Let's say you're trying to classify some input into one of 10 possibilities. We will have 10 outputs. But the way we define it is going to be using something called a softmax function, which we're going to cover on Monday.
Okay. Coming
So
up.
for now, we just live with binary classification.
Is there a default activation method in Keras, or you have to put something?
That's a good question. I believe the default might be relus for hidden layers, but I'm not 100% sure. Let's double check that. Yeah.
Just to get a clearer understanding, when you
We
said
sure that was
that
3 to 4 days
beyond
for you?
16, when you tried working on those neurons, the performance worsened. So that is where you were playing around with initially 2, and then maybe 4 and 6 and 8.
Exactly, right. Could use the microphone, yeah.
Do we need to define each of the hidden layer when the model gets more complex, when we have more than one layer? Like,
Oh,
is there a
like if you have like 25
function that
layers.
consolidates, yeah.
Yeah. So what we typically, good question. If you have, let's say 100 layers, right? Do you actually have to type in each by hand and cut and paste? No. You can actually write a little loop, which will just automatically create them for you. And so basically what's going on is that this little output thing you see here, this variable, this output could be the result of a 1,000-layer network with all sorts of complicated transformations going on. And then finally it pops up as a little thing called the output. And what Keras will do is it'll be like, okay, this model has this input and has this output. But boy, this output came from incredible transformations applied to the input.
Someone already wrote all this code for you.
That very easily for you. You don't have to worry about it.
Crazy.
Right? It's really a beautiful example of the power of abstraction. And you will see that as we go along. Okay, so now let's switch gears and say once you've written a model like that in Keras, how do you actually train it? Okay? Now, training is something you've been doing a lot, right? So for example, when you have something like linear regression, right, where you have all these coefficients you need to estimate, you have this model, then you have a bunch of data, then you run it through something like LM if you use R, and what it gives you is actual values for those coefficients, right? 2.8, 0.9, and so on and so forth. So the role of the data is to give you the coefficients.
So right? I've done linear regression at work before, unknowingly though. Now, it was a linear model, right? This is I kind of like am able to pick up on this stuff because I've kind of done it before. I've applied it before, like without actually knowing it and having learned it in a class kind of. So I talked about this before, is we had all of these individual constituents, X1, X2 were for serums. And I met with this guy who was a computer scientist, and I explained the chemistry behind it, and he helped me out with the programming, and then we built a Python program together that did this, and then and it gave us the coefficient values for the blend, how much to multiply, by the concentrations for volume, to giving you your blend amounts to do your formulation. So, this is definitely familiar.
And so on and so forth. So the role of the data is to give you the coefficients.
That's like kind of
right?
just
or you can think of the coefficients as really a compressed version of the data. Okay. Similarly, if you do logistic regression, you have a model like that. You add some data. You run it through some estimation routine like GLM or scikit-learn or stats models. Pick your favorite tool. Then you'll come up with something like that. So basically, what's going on here is training simply means find the values of the coefficients so that the model's predictions are as close to the actual values as possible. That's it. Okay. And to find the one that is as close to the actual value as possible, a whole bunch of optimization is involved. You don't have to worry about the optimization when you did regression, linear or logistic, because it's all done under the hood for you. But for neural networks, we'll actually get to know how it's done. Okay, because it's important. Okay, so training a neural network, a deep neural network, even GPT-4, it's basically the same process as what you do for regression, right? You're just a very complicated function with lots of parameters, but ultimately, you have a network with all these question marks, you add some data, you do some training, and boom, you get some numbers.
You may get into this, but are we determining the architecture of the network before we train it? Okay.
Yes, because if you don't define the architecture, Keras doesn't know how to actually calculate the output, given an input. And unless it knows input-output pairs, it can't do anything more with it.
Got you.
Okay, so the essence of training is to find the best values for the weights and biases. And the way we think of the best values is that we basically set up a little function, and this function measures the discrepancy between the...
Okay, so he says, the essence of training is to find the best values for weights, for the weights and biases, those that minimize a function that measures the discrepancy between the actual and predicted values. These functions are called loss functions in the deep learning world. These functions are called loss functions in the Okay, cool. So remember, we're taking our output, we're evaluating that difference against our output against our expected. We have a discrepancy, right? For we're supposed to get a 3 for this NIST data set output, and we got like a 4 or whatever. We would do an evaluation. We were off by a unit of 1, and then we would feed that loss function into an optimizer. Optimizer then would do whatever it's a back propagation through the algorithm or whatever whatever the network. I'm sure we're gonna get all into that, and whatnot. Cool.
We set up a little function, and this function measures the discrepancy between the actual and the predicted values. Okay, and I use the word discrepancy because the way you define the discrepancy, there is incredible amounts of creativity in the field. In fact, a lot of breakthroughs in deep learning come because people define a very clever measure of discrepancy, and then it turns out it actually gives you all sorts of interesting behavior. Okay? That's why I use the word discrepancy as opposed to the word error, because when I say error, you might be just thinking of something like predicted minus actual. That's too limiting. Okay? Prediction minus actual is too limiting. That's why I use the word discrepancy. So we basically define a function that captures the discrepancy between the actual and the predicted values. And these functions are called loss functions in the deep learning world. And every paper that you read, you will find interesting loss functions. There are hundreds of loss functions. Enormous research creativity goes into defining these loss functions. Okay? All right, so these are loss functions. And so a loss function is a function that quantifies this discrepancy. So let's say the predictions are really close to the actual values. The loss would be what?
10 to 0.
Close to 0, right? Very small. And if you have a perfect model, perfect crystal ball, what would the loss be? Exactly 0, right? Exactly 0. So in linear regression, the loss function we use is called sum of squared errors. We didn't call it loss function because we were not doing deep learning, just linear regression, but that's basically the loss function, right? So the loss function we use must be very matched very properly with the kind of output we have, right? So if your output is a number like 23, right, you're trying to predict demand, like a product demand for next week for a particular product, and the predicted value is 23, the actual value is 21, it's okay to do 23 minus 21, 2 as the discrepancy, right, the error, okay? But for other kinds of outputs, it's not so obvious what the correct loss function is, what the correct measure of discrepancy is. And so here, for the simple cases regression, right? And so here,
so mean squared error, right? So these are loss functions for determining discrepancies between output and expected data. So if you guys remember, we talked about mean squared error in the MIT course, Introduction to Computational Thinking and Data Science. That's why I took that course. You guys might have been thinking, why did he take that course like a year ago or 6 months ago when we haven't even finished it yet. We got to like the last like 2 or 3 weeks. We got the gist of it though. There's a lot of like a review, honestly, and the Python, the programming practice projects weren't very hard for me, so I didn't really finish the course. And so it was very, very basic class setup and stuff. But we did these things where you have the 1 over the n of the sum of the difference in the data point values, right? So you have, imagine like a function curve. You're fitting like a line to a function curve, and you're calculating the distances of the points away from that fitted line. And then that kind of gives you, I believe that's this function here, right? So we have some examples. One would be the mean squared error, MSE, loss. Right, this is commonly used for general numerical outputs. Okay. And then we'll take a picture of this. Bring it into our... Okay.
For the simple cases regression, right? The I here, by the way, is a superscript, which stands for the ith data point, So what I'm saying is that, okay, for the ith data point, this is the actual value, y, and this is what the model predicted, okay? I take the difference, square it, and once I square it for each point, I just average all these numbers to get an average squared error, i.e. mean squared error, MSE. So this is sort of like the easiest loss function.
Yeah, average of both the sum.
Okay. Now let's crank it up a notch. In the heart disease example, the neural prediction model, the prediction is a number between 0 and 1, right? It's because it's coming out of the sigmoid. It's a fraction. The actual output is a 0 or 1, one of the two, right? It's binary. So how would we compare the discrepancy? How would we measure the discrepancy between a fraction and the numbers 0 and 1, right?
How would we measure the discrepancy between a fraction and the number 0 or 1? Well, I mean, you kind of have like an all or nothing approach. Like a fraction, you can't really have fractional, oh yeah, he might have some heart disease in a year, right? Or has a high chance of having heart disease. You're wanting a 0 or a 1, right? And so obviously we're using in this example is a sigmoid for this final function here. Is that what he's going to get to?
Right? What is a good
But my question is okay, if fractional data, like, it doesn't really matter in terms of output, like, it's kind of like that's not the output we're looking for. Well, if you got fractional data, it's considered a zero, whereas a 0 or 1 is considered a 1, like true, like that's the answer. So it's kind of like an all or nothing approach, maybe.
The discrepancy between a fraction and the numbers 0 and 1, right? What is a good loss function in the situation, right, is the key question. So let's build some intuition around this. And let's see if my little daisy chain iPad thing works. I'm doing it on the iPad so that people on the live stream can see it. Otherwise, the blackboard is a little tough for them. OK, so let's have a situation here. OK, so let's say that you have a patient who comes in, and let's say they have heart disease. OK, so for that patient, y equals 1. Right, the true value is 1 for that patient. And now you have this model. OK, and this is the predicted probability from this model. Can people see my handwriting OK? Good. I could have never been a doctor, right? So 0, OK, 1. It's going to be between 0 and 1 because of probability. And then this is the loss we want to sort of have, right? This is the loss. So for this patient actually had heart disease, y equals 1. So let's say that the predicted probability is pretty close to 1. OK? What do you think the loss should be?
Small. Close to 0.
Small.
Sorry? Close to 0, exactly. So here, if the prediction comes here, you want the loss to be somewhere here. But if the predicted probability is pretty close to 0, even though the patient actually has heart disease, what do you want the loss to be?
High.
Really high, because it's screwing up badly, right? So you want the loss to be somewhere here. So basically, you want a function that's kind of like that.
Okay, so okay, that makes sense. That it's just as simple as, okay, in terms of, you can just kind of plot it out. Like you need to find a function, a loss function that has some sort of resemblance to this sloping effect, where the closer you get to 1, the higher of a probability of having heart disease, right? And it kind of has that ramp factor in the middle. Now, it's interesting. I wonder, like, different ramp factors. Obviously, how you determine a loss function and tweak it, and the slope and ramp of the actual loss function could affect, like, how things are trained and whatnot. So there's always different tweaking maybe they can go on to, right?
You want the loss function shape to be like that. High values of probability should have low losses. Low values of probability should have high losses. Yeah?
I understand, like, why it has to be increasing or decreasing, but can you explain why it has to be?
Yeah. So it can be linear. It can certainly be linear. But basically what you want to do is, the more it makes a mistake, the more harshly you want to penalize it, right? So basically what you really want is something where, if it basically says this person's probability is, say, the predicted probability is, say, 1 over a million, basically 0, you want the loss to be like super high, so that the model is like, it's like a huge rap on the knuckles for the model. Don't do that. That's basically what we are doing. And I'm sort of demonstrating that dynamic by using a very curved and steep loss function. But you can absolutely use a linear function. It's totally fine. It won't be as effective for gradient descent later on, but for a bunch of technical details. Are we good with this? All right. Yeah. So now let's look at the case where a patient does not have heart disease. Y equals 0. Same setup. OK?
OK.
Predicted probability, 0, 1, loss. So for this patient, they don't have whatever. They don't have heart disease.
Signs of heart disease.
If the probability is close to 0, what should the loss be? Close to 0. It should be somewhere here, right? And the more and more the probability gets closer and closer to 1, you want to penalize it very heavily, which means you want the loss to be somewhere here. So you basically want a loss, ideally, that's kind of going up like that and climbing higher and higher. Are we good? OK, perfect. Because we have a perfect loss function for that. So just to recap, right, this is what we want. People for points with y equals 1, lower predictions should have higher loss. We want something like that. And then turns out there's a very little simple loss function.
Literally just uses
the logarithm we should get the job done. So what you do is you literally do
Good job,
minus
Camus.
log of that predicted probability. That's it. And that thing has exactly that shape. Okay? And in fact, you can see it numerically. So if the loss is 1, it's 0. If it's half, it's 1.0. And if it's like 1 over 1,000, it's almost 10. If it's 1 over 10,000, it's going to be like much higher, right? Very high losses. Okay? So minus log probability. Boom, done. Similarly, this is what we want for patients for whom y equals 0. And it turns out, if you do minus log 1 minus predicted probability, it does the same thing.
Yeah, and the inverse of the predicted probability.
Okay. Mathematicians once again saved with the logarithm.
Okay, so we can capture this in a log function, right? So for our example here, so for the example of the predicting heart disease, right? We would want a, if a patient is showing if heart disease equals to true, right? How can we define this? Like, heart disease equals to true, right? It would, they have a 1 for heart disease. So if we have, the closer we are to 1 in the x-axis, we have low loss because this is true, right? I'm not really sure how to like take notes on this. We can capture this requirement using a log function. For the okay, I'll just take a screenshot. Let's take a screenshot for reference, and we'll also do a screenshot of the next one as well. Okay.
It does the same thing. Okay? Mathematicians once again saved with the logarithm. So, see, in summary, this is what we have, right? For data points with y equals 1, we have this. Data points with y equals 0, we have this. But it feels a little inelegant to say, well, if it's y equals 1, I want to use this. If y equals 0, I want to use that, right? There's like an if-then thing going on here. And I don't know about you folks, but if-then really irks me mathematically because you can't do derivatives and so on very easily. Okay? But no worries. This is MIT. We know we have our bag of math tricks. So what we do is we can actually combine them both into a single expression, okay, like this. Okay? And here the yi again is the ith data point. Remember, yi is either 1 or 0 always. And this.
Okay, so let's think here. We have no, that's not this. We're combining the two formulas of the previous statements, the previous expressions. So here, right? Okay, so we're saying if both of these equal to loss, right, we can set these equal to one another. No. The minus log predicted probability. So minus log of predicted probability Okay, so minus the y to the ith log predicted probability at the ith data point minus the inverse of the probability what does the negative y to the ith mean again? Actual value of the data point. This is the predicted. Okay, yeah, that's right. So the actual value that we're trying to. Okay, that would mean, yeah. So the actual value, right, that we're solving at this, for this prediction. Well, the actual prediction probability was. So we just take the difference of these two losses. Right? That would make sense. So what's happening is we have an actual, or like the label, the training label, what we're trying to actually solve for, the predicted probability of this run, right, for the y1, so we can just kind of stick this all together rather than having like an if else. So I'm guessing then, let's say that the predicted probability let's say that y is like, okay, because if it's 0 or 1, if it's 0 here, this evaluates out to 0. This evaluates out to just that, 1 minus 0, right? For true or false, because that's what we're solving for, y equals 1 or y equals 0, right? So if y equals to 0, this left portion of the minus sign evaluates all out to 0, whereas this just evaluates to the y equals 0 portion. That's how they're doing it. And then kind of combining the if then logic across this minus sign, because you're using multiplication, or using 0, which will cancel out either side. So if it's 1, you do 1 minus 1, which would be 0, which would cancel out this side because y is 1. So you use this side, right? That makes sense. Okay, I got it. I got it. Right. So we'll say we can combine the two loss scenarios to avoid a if-then statement, which is bad for derivatives, etc. Where if y equals to 1, heart disease is true, we use the left half, and if y equals to 0, heart disease false, we use the right half. Cool, that makes sense.
Into a single expression, okay, like this. Okay, and here the yi again is the ith data point. Remember, yi is either 1 or 0 always, and this model of xi is the predicted probability. Okay, so, and I've just taken the minus log, the minus, and I've just moved it here. Okay, and I've taken the minus that was here and just moved it here. Okay, that's why you see it like this. So this one is basically you can convince yourself what happens. This single expression will get the job done. So let's say there is a patient for whom y equals 1. What's going to happen is that when you plug in y equals 1, this becomes 0. The whole thing will collapse to 0.
Oh, he's
While
just explaining
here,
what we
y
figured
equals
out.
1 just means it becomes minus log probability.
Look at
this
us.
is what we want. Conversely, if y equals 0, this whole thing is going to disappear.
We're jumping the gun, y'all.
And this thing becomes 1 minus 0.
That just shows that we're getting
1,
it. We're
and
understanding.
so it becomes minus log 1 minus
It's a good
probability.
sign. These are
which is
good
again what
green
we want.
flags.
Simple and neat, right?
Wouldn't that make lecture so much easier if you could just pause the lecture in person and just like and think it through rather and then he explains right after?
So in one expression, we have defined the perfect loss. No if-thens, none of that crap.
None of that crap.
Good. So now what we do is, that was true for every data point, but we obviously have lots of data points.
So now we
just
combine the
add them
average.
all up and take the average.
Got you. So now we just do the mean squared average of the loss, right? That's what we're computing here. Right. Mean squared error of the loss altogether. So now taking it a step further, we'll do this. And we say combine. We can now combine the loss function scenario with the total like mean squared error loss like idea or function expression loss function, right? Because, well, it's interesting. So we're doing, this loss is called binary cross entropy. So this isn't mean squared error here. This is a different concept. Is this because it's binary cross entropy? It's all or nothing, yes or no? In terms of entropy, everything is interacting. It's all being summed together, right? And binary, it's 1 or 0 for the indication of which side of this expression you use. Is that kind of why it's called that? So is this? Oh, right. So it's not mean squared error. It's only mean, right? Because there's no squaring going on. That would make sense, right? Yeah, exactly. Thanks for clarifying that. So it's not. So we can now combine. So now we can now average this across. We can now average this across all n data points, right? Given this expression here. And so this is going to be called, what you guys were saying is just the binary cross entropy. This is called, quote, binary cross entropy. We'll find out if that's true. Maybe?
Okay. Behold, this is the binary cross entropy loss function.
Hey! Dude, I gotta stop pausing this thing. I gotta stop pausing. This thing, we are really learning. This is going good. This is awesome. That's what's nice about doing this with chat is you really
edit
learn.
the loss function so that you penalize like false negatives more strongly than false positives.
You can do all of them. Great question. I'm just looking at the basic case where it's symmetric loss. You can actually penalize overestimates much more than underestimates and things like that. And if you're curious, you can just Google something called the pinball loss.
Pinball loss.
Okay. Any other questions on this? So when you see this massive deep neural network built by Google for doing something or the other, if it's a binary classification problem, chances are they're using this thing. Okay? All right. So
Cool.
now let's figure out how to
finally have a
minimize these
definition
loss
out of that.
functions. because the name of the game is to find a way to minimize these loss functions.
You want to minimize these loss functions.
Now, loss functions are just a particular kind of function. So we'll first consider the general problem of minimizing some arbitrary function. Okay? And once we develop a little bit of intuition about that, we'll return to the specific task of minimizing loss functions. Okay.
So loss functions are just, I suck at typing, particular kind of function. So we will first consider the general problem of minimizing an arbitrary function. Loss functions are just a particular kind of function, so we'll first consider the general problem of minimizing an arbitrary function. After we develop some intuition about how we do this, we will return to the specific task of minimizing the loss function particularly. Okay, got you. We don't really need to take notes on that, actually.
How's everyone doing? Yes? No? Good? Bad?
Good.
You have a bit of a, like a tough to interpret head shake.
It's more like, I kind of lost you where you said that the loss function and the predicted probability, how were they inversely? Because the understanding was that the loss function is supposed to be the sum of errors. We are averaging the errors. And when you said the hard patient.
No, sorry. Let's just stop there for a second. For each point, you define the loss. That's the whole point of the game. And once you define it, you calculate for every point and average it, right? So just focus on a single data point. And so now continue.
So now when the heart patient there is more probability that So when there is a person who has the heart disease, you said that you want the loss function to be high. I think I'm going back to the graph.
You want the loss function to be high if I'm predicting that they basically don't have heart disease. If the prediction is close to 0, the predicted probability is close to 0, then I'm badly wrong. Because in reality, they do have heart disease. And that's why I want the loss to be really high.
Okay, so effectively loss is my way of finding out how good my model is.
Correct.
Instead of saying, okay.
Or rather, how bad your model is.
Yeah.
Right? How bad is it? That's really what the loss function is.
Got it.
And you want to minimize badness. That's the whole point of optimization.
Okay. AJ says, until now, we know only 2 loss functions, right? Yes. We've learned 2 loss functions so far. One is mean squared error loss, and we've also learned about binary cross entropy. So he says that MSE for predicting a continuing value like temperature. That's good. So we'll say like examples. Predicting a continuing value like temperature. And then we have which would be good for classification. Cool.
Okay.
This is a good lecture.
I guess I don't have a fully, similar to the point raised before, I don't have a fully clear intuition of why exactly a loss
that's just what we've learned so far, I
something
think.
that's, say, flatter for small and then really steep later.
Those are all fantastic things. You can totally do it. The reason we pick this function, because A, it's easy to work with. It has good gradients. It's well behaved mathematically. But there are many alternatives to it. I don't want you to think that this is like the only game in town, or it's the only choice for us. We have many choices. This happens to be a very easy choice, which also happens to be empirically very effective. And I'm happy to give you pointers to other crazy loss functions, right, which can actually do all these things too. Okay.
Cool.
All right, so minimizing a single variable function, we will warm up by looking at this little function here, okay, which is what do you call a 4th power? Quartic, right? Yeah, thank you, quartic. So yeah, it's a quartic function.
Say we want to minimize
right?
this function.
And this is how it looks like.
How can we go about it?
But you can see there is like a minimum somewhere here, right? Between like -1 and -2, maybe -1.5, okay?
Yeah.
So we want to minimize this function. It's obviously a toy function, a little function with one variable. The intuition we use here is going to be exactly what we use for GPT-4.
So if we want to minimize this function, does that just mean, do we want to find the lowest point in the function, or are we trying to reduce the function, or are we trying to rework the function into a different visual interpretation that's minimized? That's my questions that are going on in my head right now that I'm hoping to get answered here.
So pay attention. So how can we go about minimizing this function? What will we do?
Because if we're trying to find just the minimum of the function, right, we could just test x values, right, going through the function and finding corresponding y values that are the lowest points. You know, basically a similar approach to, so we've kind of learned to the theory behind some gradient descent as we move along the negative derivative, whatever, of this line, right? So, you know, yes, let's keep on.
Yeah.
Take the derivative and set it equal to 0.
You take the derivative, exactly. So you take the derivative, right? So let's look at what the derivative does for us. But then the second part of what said, second part of what said was set it to 0. Setting it to 0 becomes problematic when you have very complicated functions. It's not clear at all what's going to make them 0, right? Unfortunately. But the idea of taking the derivative is, in fact, the right idea. So we can go about this. We can calculate the derivative, and that actually happens to be the derivative. You can convince yourself. And if you plot the derivative, it looks like that. And as you would hope, wherever the minimum is, in fact, the derivative is crossing, right? Derivative is 0 here. It's crossing the x-axis, right?
So we're trying to find a point W which lies along our x-axis for this function g, right? We're trying to find a point on this function g that intersects with the x-axis at 0. I mean, sorry, with the y-axis at 0. Right, we're trying to figure that out. Now, the initial guy said, why not just put in 0 for your answers, your left-hand side? Well, that would just go all the way out to 0, and you get like plus 10w. But if you plug in 0 for the x, that's not really what you're wanting to do, because you would get 0, 0, but we actually have a lower point on that curve. See, a calculus, I guess, using the second derivative to evaluate if there's a minima or maxima. You'll understand better when you get the parameter update equation. Okay, let's see. Let's just keep going.
Right. In this case, we can actually do that. So let's say you have the derivative. How can you use it? Like, what is the value of a derivative? What does it tell you? Yeah.
Do you use a gradient descent algorithm?
You are 10 steps ahead of me, my friend. I just want a basic answer. Like, what good is a derivative? What does it tell you? When you calculate the derivative of something at a particular point.
It tells you the rate of change of the function at the place you are.
Correct, exactly right.
Yeah, it tells you the slope or the rate of change
what the derivative
at that
tells
point
us
in the
is
function.
that the slope tells us a change in the function for a very small increase in w, right?
Yeah, for a very small.
This is high school calculus.
Just a nudge.
I'm just doing a quick refresher.
He said, this is high school calculus, MIT. Come on, guys.
What that means is that if the derivative is positive, what that means is that increasing w slightly will increase the function. So if you're here, you calculate the derivative, the slope is positive, it means that if you go slightly in this direction, the function is going to get higher, right? Similarly, if it's negative, let's say here, you calculate the derivative, the slope is like this, it's negative, which means that if you increase w, if you go in this direction, it's going to decrease the function. Okay?
Yeah.
All right. And if it's kind of close to 0, it means that changing w slightly won't change anything. So if you're here, changing it slightly won't change anything. All right? That's it. So what we do is, this immediately suggests an algorithm for minimizing GW, which is, let's start with some random point W, and then let's calculate the derivative at that point. And once we do that, there are 3 possibilities. It could be positive, negative, or kind of close to 0. And if it's positive, we know that increasing W will increase the function, but we want to decrease the function. We want to minimize it, which means that we should not be increasing W. We should be doing
increasing
what?
W.
Yes. And similarly, if it's negative, what should we do here? Exactly. So in the first case, you reduce W slightly. In the second case, you increase W slightly. And if the thing is close to 0, you just stop because there's nothing else you can do.
Yes, because we want to reduce the loss. And if we're at 0, we're at the minimum. Okay. Yep, that makes sense.
This is the basic intuition behind how GPT-4 was built, which is kind of shocking if you think about it. Right?
High school calculus.
Which means that all the
the
heavy-duty optimization stuff that people have figured out over the decades is kind of not used. Right? This algorithm is what's being used with some, flavors on top of it. So yeah. So back to this, and you do that, and then if you've sort of run out of time or compute, or right, if you're run out of time and so on, just stop. Otherwise, just go back to step 2 and try again. Of course, if it's close to 0, you got to stop anyway. Yeah.
Is there the concern of a potentially local minimum there?
It's coming. Okay, so that's the function. It's going to find you some point where the derivative is kind of close to 0. Okay, so this is called gradient descent, right? This is gradient descent. This little algorithm, and this very PowerPointy MBA table can be collapsed into this little expression. This basically says, calculate the derivative, multiplied by a small number, which we'll get to in a second, and then change the old W to the new W is the old W minus a little number times the gradient. So this little one-line formula is basically gradient descent.
Gotcha. Right. This is really tying together what we read about in deep learning with Python, right? That's why I wanted to watch these lectures, is because we read the book, we got some exposure through some additional videos, and now this really helps tie things all together, right? We have a function, f of x or whatever. For any point x, if we move x plus some small amount, and we take the slope of those 2 differing points, that will be the rate of change between at that specific kind of window of that function. Think of like a circle, how if you zoom in really, really close, it kind of looks like a straight line. You don't really see that curve. That's why, with planets, how they're so large, the horizon looks like a straight line. You don't have the perspective zoomed out enough to see the full curve. So if you take the derivative of the Earth, right, it's such a big circle from your perspective, you're so zoomed in, you take the derivative of the horizon, of the sunset or whatever, it's mostly going to be 0 from your perspective. So it's going to be like, flat or whatever. So it's kind of an interesting analogy. Flat earthers and teaching a flat earth theory with the calculus, gradient descent. I've always had this question, why don't we just reduce the error between the actual and predicted instead of doing gradient descent? Well, off the top of my head is if you tweak one little node parameter, the whole point of gradient descent is seeing how that one weight affects all of the weights of the surrounding environment, right? Or how that one weight actually impacts your final result. And if you have a bunch of weights, it kind of descends through this entire mapping, evaluating, of each specific instance, how it contributes to the final result, and if you have greater weights tied to various edges, then there is, more impact for that. So tweaking that value causes greater fluctuations in your results. So I guess, and it kind of can learn that this has a large impact at this specific node step for this specific trait example or whatever, Yeah, if you relate it to the loss, basically, the loss is a function too after doing the forward pass for the neural network. Gotcha. All right, let's keep on.
Okay? And what you should do, just to build your intuition, is to make sure that these and one level, which will get very good. Go to find stop anyone. Run up, yeah, stuff. Similar, do you want here me go in this calculator, right? What is the function? In this direction, if you're here, you calculate in this direction, it's going to.
Okay.
Yeah.
Is there the concern of a potentially local minimum there?
It's coming. Okay, so that's the function. It's going to find you some point where the derivative is kind of close to 0. Okay, so this is called gradient descent, right? This is gradient descent. This little algorithm, and this very PowerPointy MBA table can be collapsed into this little expression. This basically says, calculate the derivative multiplied by a small number, which we'll get to in a second, and then change the old W to the new W is the old W minus a little number times the gradient. So this little one-line formula is basically gradient descent. Okay? And what you should do, just to build your intuition, is to make sure that these three possibilities here map nicely to this. Like this thing will actually capture these three possibilities. Yes, gradient descent was invented. You need to have some historical fun, right?
2016, 2012, 1970?
19th century. Yeah, okay.
19th century.
Good, very good. Excellent guess. 1847.
Way long ago.
It was invented in 1847 by Cauchy, the great mathematician. And in fact, if you're curious, you can check out the paper.
I thought I mentioned. I thought that was earlier than that.
I give you the paper here for handy reference.
Dang, man. People are smart.
So 1847.
What happened to us?
So GPT-4 was built using an algorithm invented in 1847, which I find like astonishing, frankly.
It's just crazy.
This little thing is so capable. Okay, so that's gradient descent. And this little number alpha is called the learning rate. And it's our way of sort of essentially quantifying the idea of let's not increase or decrease W massively. Let's do it slightly.
Okay, so alpha, I don't have the thing right, is called the learning rate. Right, remember this learning rate is what's applied to the loss value in order to make that nudge adjustment down the gradient descent. Now we choose a learning rate not too small or too large in order to make enough movements but not enough movement to overshoot, kind of like, and then they also talked about the idea in those videos we watch of like momentum, right? How, think of like a ball rolling down a hill is, if you have really like, if we calculate the derivative at that point is a really like high steep slope in the negative, right? So you're going down the slope, you kind of can take a larger step because you're not really reaching a bottom. You can take a large step because you can kind of ride that slide down, and then once you start to see your your slope taper to a flatter plane, you can kind of shrink your learning rate maybe, and kind of have a function of momentum to increase and decrease your learning rate to kind of mimic that momentum, right? So it's multiplied against the gradient. So that it already apply. Okay, interesting. So it's apply. It's yeah. Sorry. So it's being multiplied against the gradient. So it already has that effect. So if you have a okay, yeah, right. That would make sense. So the magnitude is already being multiplied against the gradient here, which is your derivative at that point. So if you have a really steep thing, you're going to move a lot faster. Now, do you ever see people adjust the alpha value as well mid gradient descent? Do you see people shrink or abstract or contract the alpha value or grow it depending upon this, or does that magnitude by default kind of do enough? That's my question. We're asking the right questions here. We're learning this. Oh yeah, that's what it was in 2016, Casper, the AlphaFold stuff. That's right.
Because the gradient is only valid for small movements around your point. If you take a big step, all bets are off. So this alpha tells you how small a step should you take. Okay? And typically, it's set to very small values like 0.1, 0.01, and so on and so forth. And in fact, if you read any deep learning academic papers where they have trained like a big model to do something, right? A lot of researchers will very quickly go to the appendix where they have described exactly what learning rates were used.
This is a really good lecture. I'm learning a lot here. This is awesome. So the alpha A is called the learning rate. Is our way of ensuring that we increase or decrease the weight slightly. So it is being multiplied by against the gradient, the derivative slope, set point. And it's being multiplied against the gradient at that point. And as a result, steeper gradients cause larger movements, and as the gradient tapers off, the steps shrink to approach the minima. Boom! Look at us. It's a hyperparameter you evaluate based on the values you do during training.
Will very quickly go to the appendix where they have described exactly what learning rates were used. Because sort of the learning rate is like part of the IP for how it's built. There's a lot of trial and error that goes into these learning rates. Okay, so that is gradient descent. So if we apply this algorithm to GW, our original function, right? We just keep on doing this thing a few times. Right?
Yeah.
What you will find is that if, let's say we start with the point we randomly pick is at 2.5, we set the alpha to 1.
This is a good chart.
We run this algorithm, it starts here, then it goes there, boop, 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 and then finally ends up here.
This is
in
a good
like
chart.
4 or 5 iterations, it finds a minimum.
I like this chart. This is a good chart. I like that boulder. That is a nice boulder.
This is obviously a very simple, well-behaved, nice little function, so you can easily optimize it.
Yeah, it's not like a surface or some multi-dimensional
You can just go to this thing. There's a nice animation of this thing.
It's just a line, right?
Okay, so now, all right, before we actually go to the multivariable function, I want to go to the question that you posed about local minima. Actually, you know what? I think I may have some slides on it. So sorry, I'll come back to this. So let's actually see what we looked at a toy example where there is only one variable. What if you have, what if it was GPT-3? GPT-3 has 175 billion parameters. 175 billion, and GPT-4, they haven't published it, so we don't know. It's supposed to be 8 times as much. Okay? So, I mean, the number of parameters is massive. So basically, our loss function has billions of variables, billions of W's that we need to optimize over, minimize over. So we need to use this notion of a partial derivative.
Crazy.
So
You can't even
let's take
comprehend
baby
the
steps
scale.
and say, okay, what if you have a 2-variable function, right? Something like this, very simple. So what we can do is we can calculate the partial derivative of g with respect to each of these W's. And the partial derivative, just to quickly refresh your memories, is you take a function, you pretend that everything other than W is a constant. Then the function becomes a function of just one variable W, W1.
That makes sense. Okay, so that's something that I don't really remember from calculus that well. It's been like, 8 years since we took that in class. So, you can take the partial derivative, take the partial derivative, right? For a point, for a specific weight, like, because if you have multiple, this is the part that gets tough here.
And then you just differentiate it like you do everything else. And you get something, and that is this thing here. And then you do the same thing for W2, you get this thing here, and then you just stack them up in a nice list. Okay?
So we have a multivariable function g, w1 and w2, which is w1 squared plus w2 squared plus 2. We calculate the partial derivative of this function, right? The partial derivative of g over partial derivative of g1, right, with respect to g, or whatever, partial derivative of g with respect to g with w2 equals to these partial derivative values. So to the partial of a point of the function with respect to the weight slash point. For partial derivatives are taken by holding all other variables constant and solving a derivative for a single variable, the one you are focused on. So it looks something like this. Take the partial derivative of data points with respect to each other, with respect to each parameters. Okay, so it's not with respect. So how does the phrasing go? It's take the partial derivative of the function on the data point with respect to each parameter. So it's you take the partial derivative of the data point of the function at that point. Take the partial derivative for a function at a point with respect to each of other parameters, with respect to the other. With respect to the other parameters.
This is the vector of partial derivatives. So how should we interpret this? The same way as before. Basically, for a small change in W1, keeping W2 and everything else fixed, how does the function change if we change just W1 slightly? And similarly for W2 and all the way to W175 billion.
The first number is the change in G of W for a small increase in W1, with W2 kept unchanged. Yes, the second number is the change in the function for a small increase in W2, with W1 kept unchanged, right? You're just holding all other variables constant in your expression, your multivariable function, 2, 3, 4, 5, 6, a billion variables. You're holding all of them function, and for that ith variable that you're looking at, you're taking the derivative at that variable with respect to all the other variables held constant. And that is being just here in just this list of this vector of partial derivatives. Cool, pretty easy. Vector of partial derivatives. So we say the first number, 2W1, is the change in G of W for a small increase in W1, with W2 kept unchanged. The second number, 2W2, is the change in G of W for a small increase in W2, with W1 kept unchanged. Cool. Let me go get a refill on my Mountain Dew skis, boys. If you haven't liked and subscribed to the stream so far, make sure you do so. We're doing MIT's OpenCourseware's Hands-on Deep Learning Spring 2024 15773 course. We're on lecture 2 right now. We're also doing this paired with the Deep Learning in Python book. We've read up to chapter 2 in that book, which covers intro, coverage, and neural networks, and gradient descent and whatnot. So this lecture is really giving us some solid overview and solidification of what we read in that book. And so I'm feeling a lot more confident about what we've learned so far. But we have about 30 more minutes left on the video, so let me go grab a refill here and we'll keep going. Like, subscribe if you haven't. Alrighty. Got a refill. Let's keep it rolling. Hope you guys are enjoying the stream so far. If you guys are learning some stuff, leave a like. Let me know how you guys are learning. Let me know what you're learning, what you're building. Thank you so much for being here. We're an hour and 42 minutes in the stream, but we've only watched 45 minutes of the lecture. We got to keep moving.
It's the same thing, okay? So now when you have these functions with many variables, many w's, since we have a gradient for each one of those w's, we stack them up into a nice vector of derivatives, and this vector is called the gradient. And it's denoted using this, anyone know what the symbol is called? Yeah?
Laplacian.
Maybe that's a synonym, but the one I'm familiar with is nabla.
Nabla.
Delta is the one that's upside down triangle, but I think the upside
Freddie.
down triangle is called nabla, if I recall. Am I right? Thank you. He's my go-to.
That's my quant.
So yeah, so the gradient, we just call it the gradient, and it's written as this. All right, so what we do is we simply do gradient descent on every one of the w's using its partial derivative. Okay, so in a gradient step, we update w1 using this formula, w2 using this formula. Finished. We have just generalized gradient descent to an arbitrary number of variables.
So my question is that's what I don't get. So you have a gradient, which is a vector of partial derivatives, and then do you go through that vector or that list of partial derivatives and update w for every single? Yes, you would. Now, is this 2 out front? Is this just like some, like 2 via, like, that's just the 2 that happens to be the derivative of whatever this value is, 2 times 2w, whatever, right? It doesn't have any real, like, significance. It's just like, that it's just there for, like, show. But we can simply do gradient descent on each coordinate by using the corresponding partial derivative. So you would then loop through your partial derivative list. That's my question. Let me ask Jeep. For gradient descent, I'm trying to understand if once we compute the partial derivative across every weight in the network, or every value, would we then go back through, once we have our now gradient or vector of all our partial derivatives, would we go back through and loop through every weight again and update the weight value by the step times the gradient in the negative direction? So it'd be like a 2n loop. At the simplest implementation, gradient descent is often 2 continual passes over the parameters. Compute all the partial derivatives for every parameter. Store them somehow. After backdrop, you might have this. Update all the weights of those gradients. So yeah, 4 and then 4. Ah, that makes sense. Okay, cool.
Okay, so in a gradient step, we update w1 using this formula, w2 using this formula. Finished. We have just generalized gradient descent to an arbitrary number of variables. So, and of course, as before, this can be summarized compactly as this vector formula. Okay, let me just do this. So what's going on here is that I have w1, old w1 minus alpha times the function g of w1, then w2 minus alpha g by w2. And then all we are doing is we're just stacking them up into a vector like that.
I get it. It's just a 2 pass over all of the weights.
Minus alpha. And this vector is like that.
And then we would...
So this can be written as just this vector w, the new vector, old vector minus alpha, and the gradient. Finished. And you can see, if it's GPT-3, this vector is going to be 175 billion long. Okay, but whether it's 2 or 175 billion, who cares? It's the same thing, right? Okay. So yeah, so that's what we have here. I'm really thrilled, by the way, this whole iPad business is working out. So I'm a little worried about it. Okay. So if you look at 2 dimensions, this function, and if you actually look at, if you plot the function, this is W, the first W, the second W, and then this is actually the loss function. That's that function GW. And so you want to find the minimum here. And so that's how the gradient descent will
3D graphs are so cool.
If you're starting from this point. Or you can also sort of look at it from up top down into the function. And that's what this picture is. And it shows gradient descent starting from there and working its way down from here all the way to the center. OK, so all right, local minimum. So now gradient descent will just stop near, hopefully, a minimum, right? But the problem is it may not be a global minimum. It may not even be a minimum. So, so let's see what I'm talking about here. Here are some possibilities. So let's take a simple function. Okay, let's take this is GW, this is W, and turns out this function is actually looks like this.
Yeah, a bunch of wells. Like what if it has a bunch of wells in it? Yeah.
Okay. So you can see here, well, this point here is a local minimum. This is a local minimum. It's a local minimum.
Blizz, and they wonder why students are having a hard time finding work.
Here. Okay. And
it's kind of crazy,
yeah,
right?
There's a lot of local minima here too.
When that's what the teaching
these are all
that they're getting.
places in which the derivative is going to be 0. So if you run gradient descent and it stops because the gradient is reached 0, you could be in any of these places.
Yeah, you could be in any little
right?
well.
So there is no guarantee. So this in this picture happens to be maybe the global minimum because it's the lowest of the lot, right? But there's no guarantee you're actually going to get there. Okay, there's not even a guarantee you're going to be in any of these places because you could literally be in this thing here, where it's sort of taking a break and then continuing on down. That, by the way, is called a saddle point. I drew it badly, but the source of coming in, sort of taking a break and going down again, is called a saddle point. So gradient descent can stop at a saddle point. It can stop at some minima. There's no guarantee it's going to be global.
Here's a question for you guys. For people that are like into mapping or like geography or like, those types of things, if you, do they use like gradient descent to compute like trails and like, like down, if they were to do like LiDAR of, or would that be more along of like, it might not be as feasible for like real 3D, real world structures. Maybe it's better to do like, search algorithms or like path search algorithms rather than doing like a gradient descent down, like, because I'm trying, like, what if you're like, I'm trying to map like a real hill or something and you wanted to find like a direct path for the steepest, fastest way down, or like, it's interesting, like.
Okay. But it turns out it has not mattered. So it has not mattered. And there are a whole bunch of reasons why it has not mattered. Because when you have these very complicated neural networks, they're very complex functions, even finding a decent solution, right, to these complicated networks is actually really good for solving the problem. You don't have to go to the best possible solution. And in fact, if you go to the best possible solution, you actually run the risk of overfitting. So that's one reason. The other interesting reason, and by the way, this is a very hot area of research to figure out exactly. So it's sort of like this. Empirically, what we have seen is that not worrying about local minima, global minima, all this stuff has not hurt us because these things are amazing. GPT-4, probably they just stopped somewhere. It wasn't even a local minima. They're like, oh God, it's been running for 6 days. We spent $2 million. Let's stop. right? Because these are very expensive. So, but that's still so magical.
Man, we're at a local minimum. It's been running for $10 million
You don't need to
on
get
this machine.
to
Let's
anywhere
stop.
close local minimum. But there's another interesting point which
I like
I
this
read
guy,
about.
dude. He's so funny.
People basically hypothesize that for you to be at a local minimum, just think about what it means. It means that you're standing at a particular point. In every direction that you look,
it's up.
Things are just sloping upward.
Yeah, you're stuck.
Everything is sloping upward. Only if everything is sloping upward all around you could you be at a local minimum, by definition.
Yeah.
But if you have a billion dimensions, what are the odds that you're going to be standing at a point where every one of those billion dimensions is going upward?
Not very
odds
likely.
are really low. Chances are some of them are going to go going up, some of them are going down, others are sort of coming down and going another way. It's going to be crazy. So in some sense, the best you can hope for in these very high dimensional situations is probably a saddle point. And it turns out it's good enough.
That's interesting.
So for those reasons, we are content with just running gradient descent with some tweaks, which I'll get to in a second. And it just performs really admirably.
Cool.
How does alpha depend on like how much compute you have? Like, would you set the learning rate based on that, or not really?
No, the learning rate is a measure of, it's sort of like this. When you're at a point where you think that the gradient is looking nice and, right, if you take a step in the direction, it's going to go down. And if you further believe that it's going to keep going down in the direction for a while, then you're very confident about taking a big step. But if you're like, I don't know, because maybe I take a little step, maybe I have to go this way.
Yeah, that's exactly what we're talking about. That's exactly what we're talking about.
Big step because then you have to
the
back
magnitude.
So those kinds of considerations go into the learning rate. And so that's sort of the rough answer to your question.
You're multiplying the learning rate against the gradient. So larger gradient magnitude causes you to move step. That step causes you to step further.
Given amount of
just based off of that multiplicative property.
If you have a particular kind of data, you can have very aggressive learning rates.
Good question,
it tends to be a bit sort of jumbled up, complicated. So, but that's sort of the quick surface level idea of what's going on.
That makes sense.
Okay. 9:31. By the way, folks, this lecture is like probably one of the driest in the semester because of like I have to go
I think this one's great.
Once we start doing collabs.
If you think this is dry, this ain't for you, y'all. This is fun.
All right. So now let's talk about minimizing a loss function gradient descent. So here is our little binary cross entropy loss function that we saw from before.
Yeah.
Right? This is what we want to minimize. So if you look at this thing, where are the variables we need to change to minimize this function? Folks, don't look at your phones. Okay, with laptop and iPad use, don't look at your phones.
Sorry, we've kind of abstracted the variable W, but just to bring it back, those are actually the weights in the neural network,
Exactly.
right?
Yeah, the weights and the biases. I'm just calling them as weights.
So the output of these minimization functions are going to be the actual weights in our model, right?
Exactly. Okay. Exactly right.
Bro, how to tell MIT students to get off their phone. That's what's so crazy to me. That is what's so crazy to me. It's just like these experiences are wasted on people that don't take advantage of them. Like, it's just so funny. Like, these people work so hard to get into MIT. They grind their entire youth to get into MIT, and they're finally there in the lecture learning about some really advanced things, learning about some potential concepts that could make them hundreds of thousands of dollars in their career, and they're having a one-on-one interaction, not one-on-one, but 1-on-50, a very intimate interaction with one of the smartest people in the field, and yet they're on their phone. And yet they're on their phone. Like, are you serious? You beat out all of those other kids for scholarships, for admission into one of the most prestigious schools, just to go to lecture and be on your phone? I don't know, dude. That kind of irks me. That's probably true, right? They go on their phone. They probably already know it. They go to MIT, they probably already know it. Kids at my school, if they were on, they didn't know it. We're getting uncled over here. Unc Mike. Unc Mike. That's funny. Yeah. No, in hindsight, I'm sure. Like I remember, I was that guy too, right? It's just funny though, like how when you're in that moment, you don't realize it. Like it's all a 20 vision. Like hindsight's 2020. Like when you're in that moment, you don't realize like, oh, this opportunity I have, like they already know it. Maybe I was the idiot that just came to class not prepared.
The whole name of the game is to find the weights. And so, for example, when you see in the press that Meta has essentially made the weights of Llama 2 or something available, that's basically what they have done. Basically published the weights.
The reason that's so valuable is...
Microphone, please.
Because if you have a billion parameters, the compute time on that is horrendous and expensive. That's why those weights are so valuable.
Correct. The weights are the crown jewel because they are the result of a lot of money and time and smartness being spent. There is a separate question of why are they making it open source, which I'm happy to chat about offline. All right, cool. So what are the variables we need to change and minimize? It's basically the parameters, and they're hiding inside the model term, right? Because what is the model? The model is some function like that, right?
Yeah.
If you look at the simple GPA and experience thing we looked at on Monday, we finally figured out that the actual thing that comes out here is going to be this complicated function of all the x's and the w's and so on and so forth, right? And that complicated thing is showing up inside this thing. So, you know, and the w's here are the variables we need to change to minimize the loss function. And it's important for you to note and understand that the values of x and y and so on are just data.
Tim, I don't know if they're from Boston. I think that they're from overseas.
What you're optimizing is the w's, the weights. Okay, so imagine replacing the model here with the mathematical expression above whenever this appears in the loss function. And once you do that, your loss function is just a good old function of the w's. The fact that it's a loss function is kind of irrelevant. It's just a function. And since it's just a good old function of the w's, you can apply gradient descent to it as we normally would. It's no big deal. Which brings us to something called backpropagation. If you remember nothing else about backpropagation, just remember this. Never use the word backpropagation again. Only use the word backprop. Up your hip and cool to the deep learning community. Backprop. Okay? All right. So what is backprop? Backprop is a very efficient way to compute the gradient of the loss function. So when you have this loss function, and let's say you have 1 billion w's, and you have 10 million data points. So the little n we saw was 10 million. That is a lot of computation.
A lot of derivatives you have to calculate.
And that is just for one step of gradient descent, right? So backprop is a very efficient and clever way to compute the gradient of the loss function, which takes advantage of the fact that what we have here is not some arbitrary model. It's a model that came from a particular kind of neural network, which has layers one after the other, and then there was an output at the very end. So what backprop does is it organizes the computation in the form of something called a computational graph, and the book has a good discussion about it. And so what we do is we start at the very end. We calculate the gradient of the loss with respect to the output. Then we move left. We calculate the gradient of that output with respect to the output of just the prior hidden layer. Step to the left, calculate the gradient of the current thing with respect to the previous layer. You get the idea, right? It's iterative and it moves backwards. And by doing so, you never repeat the same computation twice wastefully. That's the big advantage. You calculate once and reuse it many, 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 many times. The second advantage is that if you organize it this way, it just becomes a sequence of matrix multiplications. Okay. And it becomes a sequence of matrix multiplications and eliminates redundant calculations. And best of all, there are these things called GPUs, graphics processing units, originally invented to accelerate video game rendering. And as it turns out, to accelerate video game rendering, the core math operation you do is basically a matrix multiplication, right? Some linear algebra sort of operations.
Man, dude, I wish I would have taken this class 5 years ago. Well, actually, it only came out January 2026, so couldn't have done that. But if you were just able to make the connection that the hardware needed to do these computations was going to be graphics units, and just bought NVIDIA stock 4 or 5 years ago, like, it's GG's. You don't need to work again for the rest of your life. It's over. Like, isn't that crazy? Like, if you're able to bridge that connection by having that knowledge.
And so someone really at some point had the bright idea for deep learning, calculating gradients and so on, we need to do matrix multiplications. And here is some specialized hardware that does a fast job of matrix multiplications. Can we use this for that? And they did it, and all hell broke loose. That's literally what happened. And that's why NVIDIA is valued at, what, 1.5 trillion or something? So, yeah, so they are really good.
It's just like mind-blowing, dude.
Backprop, the way you do backprop plus using it on GPUs leads to fast calculation of loss function gradients. If this thing were not true, this class would not exist because there won't be any deep learning revolution.
It's crazy.
This is a fundamental, seminal reason.
I'm so curious what it's going to look like in 5 years,
All right,
6 years.
so the book has a bunch of detail.
This is just nuts, dude. Like, man, Time Machine. It's so stupid. Like, it just seems like so simple. Like, the connection was just right there for for people to make, but just, like, obviously, if you knew about, if you were in these fields and stuff, you could have made the connection, right? It's just whether you got lucky, you hit the lottery, or and just got, the timing was right, and you were in school at the right time, right, for the right field, you would have now whether you would have pulled the trigger on the connection you made and bought the stock or whatnot, but it just seems like such like a no-brainer. Like, I don't know, in hindsight, right? Dang. By organizing the computation in the form of a computational graph, we can incrementally calculate the gradient one layer at a time using matrix multiplications and other operations. I wonder what the room was like when they first did this. Like, I don't know. Like, I wonder what the vibe was like. Vibe check for. It turns out that GPUs, originally invented for video games, are perfectly suited for backprop plus GPUs equals fast calculations of
and I actually did I hand worked out an example of calculating a gradient like the old-fashioned way and calculating it using backprop. So take a look at it. I'll post it on Canvas, and you will understand exactly where the savings come from, where the efficiency gains come from. Okay? In the interest of time, I'm not going to get into it now. All right. Any questions so far? Yep.
Sorry, I followed up too, and so we've done gradient descent, which is different than calculation of the gradient of the loss function. What is the purpose of the calculation of the gradient of the loss function?
You calculate the gradient because the fundamental operation of gradient descent is to take your current value of W, and modify it slightly. And the modification is old value minus learning rate times gradient.
So we need to, hopefully he goes over like implementation.
It'd be cool, right, if I say, go
exactly.
back 5 slides to this thing and it just goes back. Product idea. Anyone? Startups? So this one. So this is the fundamental step of gradient descent. So this is the current value at W. You calculate the gradient at that current value, multiplied by alpha, do this thing, and you get the new value. And you keep repeating.
Right, but GW, that's not the loss function.
It is a loss function.
That is the loss function?
Yeah, here I'm just using G as an arbitrary function just to demonstrate the point. But when you're optimizing, when you're training a neural network, what you're actually doing is minimizing a loss function.
Right.
Loss of W.
Sorry, I got things mixed up.
No
Thank
worries.
you.
Yeah.
How do we define the initial weights for the neural network?
So yeah, the initial weights. So there are many ways to. So first of all, they are initialized randomly, but randomly doesn't mean you can just pick any random weight. There are actually some good ways to randomly pick the weights. Those are called initialization schemes. And there are a bunch of very effective initialization schemes people have figured out over the years. And those things are baked into Keras as the default. So the Keras, I believe, uses something called the HE initialization, HE initialization, or the Xavier Gloro initialization. I wouldn't worry about it. Just go with the default initialization. And the reason why they have to be very careful about how these weights are initialized is because if you have a very big network, and if you initialize badly, then the gradient will just explode as you calculate it. The earlier layers, the weights will have massive gradients, or the gradients will vanish. So therefore called the exploding gradient problem or the vanishing gradient problem. To avoid all those things, researchers figured out some clever way to initialize so that it's well behaved throughout.
If using backprops in GPUs was so critical, I'm just curious, like, who first did it and when? Was this like a couple of years ago? Was it a company? Was it?
Yeah. Well, GPUs have been used for deep learning, I want to say. I think the first case may have been in the mid-2005, 2006 sort of thing. But I would say that it sort of burst out onto the world stage and made everyone take notice when a deep learning model called AlexNet in 2012 won a very famous
here you go, AJ.
computer vision competition. And it beat the
AJ just said this in
set a
chat.
world record for how good it was. And that's when everyone was like, hey, what is this thing? And that's really when it burst onto the world stage. I'll talk a bit more about it when I get into the computer vision segment of the class.
That would have been cool to
But you
see.
can
Like,
Google
like,
AlexNet
what
and you'll
the
find a whole
heck
bunch
is
of
this
history
thing
around
you guys just brought over here? What the heck?
Hypothetically, then is it true that if we could get to a global minima, that would mean there would be no hallucinations?
Good question. So if it is perfect, if you get to a global minima, first of all, global minima doesn't mean the model is perfect, right? It may still have some loss. But global minima is going to be on the training data. You can imagine that the test data, future data, has its own loss function, right? So what is minimum here may not be minimum there. That's the problem. Is there a comment? No? Okay.
Just
really
saying
cool
that
lecture.
That would mean that also you can be overfitting for
Correct, exactly, exactly. So if you overdo, if you find the best thing in the training function, chances are it doesn't match the best thing of the test data. So on the test data, you're actually doing badly. Okay, so come back to this. Okay, now the final twist to the tail here. We're going to go from something gradient descent to something called stochastic gradient descent. And stochastic gradient descent, or SGD, is the workhorse for all deep learning, okay? And funnily enough, SGD is simpler than GD, okay? Just when you thought it couldn't get simpler, right? Okay, so for large data sets, computing the gradient of the loss function can be very expensive, right? Needless to say, because it has to be done at every step, and the cardinality of the data set is really big, right? And you may have, I don't know, billions of parameters. It's just very, very tough to compute it, even with backprop. So the solution is at each iteration, when I say iteration, I'm talking about this step of gradient descent. Instead of using all the data, instead of calculating the loss function by averaging the loss across all n data points, and then calculating the gradient of that thing.
At each iteration, instead of using all the n data points in the calculation of the gradient of the loss function, randomly choose just a few of the n observations called a mini batch, and use only these observations to compute the partial derivative. Okay, so the solution for this, for stochastic, for large data sets, computing the gradient at each step is very expensive. Solution for this is that each iteration step of gradient descent, instead of using all of the n data points in the calculation of the gradient of the loss function, randomly choose just a few of the n observations called a mini batch.
What you do is you just choose a small sample randomly. You choose just a few of the n observations, and we call it a mini batch. So for example, the number of data points, you may have 10 billion data points, but in every iteration, you may literally grab just like 32 or 64, something
We're
really
almost
small.
there, you guys. We're almost there.
Like
Hang in there.
absurdly small.
We're doing good, gal.
And then you pretend that, okay, that's all the data I have. You calculate the loss, find the gradient, and just use that here instead. Okay? So this is called stochastic gradient descent. So strictly speaking, theoretically, SGD uses just one data point. But in practice, we use what's called a mini batch, 32, 64, whatever. And so mini batch gradient descent is just loosely called stochastic gradient descent, SGD. So an SGD, as it turns out, you can see it's clearly very efficient, right? Because it's just processing a few at a time. And in fact, if you have a lot of data and you calculate the full gradient of the loss function, all the points are used in the calculation.
The stream's lagging a little bit.
This
Sorry,
only
guys.
approximates the true gradient, right? It's only an approximation. It's not the real thing. It's only an approximation. But it works extremely well in practice, extremely well in practice. And there's a whole bunch of research that goes into why is it so effective. And people are discovering interesting things about SGD, but we don't have like a definitive theory as to why it's so good yet. We have some interesting research threads that have happened. And very tantalizingly, because it's only an approximation of the true gradient, SGD can actually escape local minima. So in the true loss function, you're at a local minimum. But in SGD's loss function, when you're doing SGD, you're reaching the minimum of the SGD loss function, which actually may not be the actual loss function. So as you're moving around, you're actually jumping from local minima to local minima of the actual loss function. I know that's a mouthful. I'm happy to tell you more. It's just a side thing that I just want you to be aware of, okay? One of the reasons why SGD is actually effective. It's almost like you work less and you do better. Like how many times does it happen in life? There's one of them. Okay? Now, SGD comes in many flavors. Many siblings. It's got a lot of siblings and variations. It's a big family. And we're going to use a particular flavor called Adam as a default in this course. And I'll get back to it when we get into the collabs and things like that.
So because not all n data points are used in the calculation, this only approximates the true gradient, but nevertheless works well in practice. In fact, because it is only an approximation of the true gradient, it can sometimes escape local minima. Wow. That's interesting. SGD comes in many flavors. And we will use a flavor called, quote, atom as our default in HODL.
Looks like that. All right. By the way, you know how all these pictures have been showing you a nice little function like that, a little bowl, and so on. This is a visualization of an actual neural network loss function. You can see like the hills and valleys and the crags and so on and so forth. Okay, and you can check out that paper to get more insight into how they actually came up with this visualization. It's crazy. It's complicated. Yeah.
So for SGD, do you perform the iterations until you minimize the loss function for each mini batch and then move to another mini batch?
Yeah, so what you do is you take each mini batch and then you calculate the loss for the mini batch, you find the gradient, and use the gradient and update the W. Then you pick up the next mini batch.
So you don't pick a mini batch and try to perform the iterations on that mini batch until you reach.
Right. Each mini batch, one iteration. Each mini batch, one iteration. Because if you do a lot of iterations on one mini batch, first of all, you'll never be sure that you're going to find any optimal solution because you're not guaranteed of any global minima. And secondly, it's much better for you to get new information constantly, because what you can do is you can revisit the mini batch later on, right? And that gets us into these things called epochs and batch size and so on, which we'll get into a lot of gory detail when we do the collab. So let's revisit that question. It's a good question. Yeah?
When you do the backprop process, it
Very
sounded
good. Backprop, not backpropagation. Nice.
I made sure.
Yes.
It sounded like you started from the layers that were closest to the output and you went backward. Okay. And my question is, are you doing that once, or is it looping multiple times? And then
Just do it
also
once.
Just once?
Yeah.
Okay.
So for each gradient calculation, you do it once.
Why does it want to start from the layer that's closest, or why do you want to start it from the layer that's closest to the output?
Yeah. So basically, what happens is, let's say that just for argument that you will go in the reverse direction, you will discover that a lot of paths to go from the left to the right will end up calculating certain intermediate quantities, including the very final gradient sort of item, again and again and again. The same thing is going to get calculated again and again and again. So by starting from the end and working backwards, you just reuse stuff you've already calculated. So that is sort of the rough idea. But if you see my PDF, I've actually worked out the example, and that'll demonstrate what I'm talking about. By the way, this the backprop is just a sort of a, like in calculus, we have something called the chain rule. To calculate the derivative of a complicated function, you calculate the derivative of like the outer function, then the inner function, and so on and so forth. The backprop is essentially a way to organize the chain rule to work with the neural network layer by layer architecture. That's all.
Sorry, is it fair to say that once we are finding like the local minimum, we are not optimizing to all the GWs, because like this local minimum is coming like from different curves, from different lines. So is that fair to say?
When we are using stochastic gradient descent, yes. So in stochastic gradient descent, when you take, say, 32 data points from 1,000,000, and you're calculating the loss for that 32 data points, you're basically trying to do a gradient step, right? The W equals W minus alpha gradient thing. You're doing it for that 32 points loss function, right? Which is not the 1,000,000 points loss function. That's why it's approximate. But the approximation, instead of hurting you, actually helps you, because it helps you escape the local minima of the global loss function. So it's a sort of an interesting and somewhat technically subtle point, which is why I'm not getting into it too much. But I'm happy to give pointers if people are interested. Yeah?
When you say you initialize the weights, you initialize for the whole network or just the end layer and then go backwards? Like
So you initialize everything in one shot. Because if you don't initialize everything in one shot, what's going to happen is that you can't do like the forward computation to find the prediction. And so they are done independently, and the initialization schemes will take into account, okay, I am initializing the weights between a layer which has 10 nodes and on one side and 32 on the other side, and the 10 and the 32 actually play a role in how you initialize. Okay, so so the summary of the overall training flow is that you have an input, goes through a bunch of layers, you come up with a prediction, you compare it to the true values,
loss
and
function.
These two things go into the loss function calculation. You get a loss number, right? And you do it for, say, 10 points or 32 points or a million points. And this loss thing goes into the optimizer, which calculates the gradient. And once it calculates the gradient, it updates the weights of every layer using the W equals W minus alpha times gradient formula, gradient descent formula. And then you keep doing this again and again and again. This is the overall flow. This is how our little network is going to get built for heart disease prediction. This is how GPT-4 was built. And this is how AlphaFold was built. And AlphaGo was built. You get the idea. I mean, it's astonishing, frankly. If you're not getting goosebumps at the thought that this simple thing can do all these complicated things, we really need to talk offline.
Agreed.
There was a hand raised here.
Yeah.
It's like really fascinating.
Just quickly, this is for each mini batch, right? So my question is, if you came with different weight for each mini batch, how do you add it up? Okay, this weight is the perfect combination for this mini batch, but you have way different weight for another mini batch. How do you combine those two?
No, at each point, what you do is you start with the weight, you run it through for a mini batch, you come up with a loss function, you calculate the gradient, and now using the gradient, you updated the weight. Now you have a new set of weights, right? Which is the updated weights. Call it W2 instead of W1. Now W2 is using your network, and when you take the next mini batch, it's going to use W2 to calculate the prediction. And this whole flow will become a lot clearer when we do the collabs.
You got to kind of see it.
So we have 3 minutes. I don't want to go into regularization overfitting in 3 minutes. So let's have some more questions. Yeah.
Can you use any activation function as long as it gives like positive values for like x squared or mod x or something?
You can use a variety of activation functions. There's a whole literature on the pros and cons of various activation functions that you could use. But in general, you have to make sure of a couple of things. One is that when you do backprop, the gradient is going to flow through the activation function in the reverse direction. And the activation function should actually sort of make sure the gradient doesn't get squished. It shouldn't get squished. It shouldn't get exploded. So those are some considerations. These are technical considerations, but those considerations have to be taken into account. If you can take those into account, then you're OK. That's sort of the key thing to keep in mind. And that's, in fact, why the ReLU is actually very popular, because as long as the value is positive, the gradient of the ReLU is just 1, right? Because so if you look at something, oops. So if you have something like this, the ReLU is like that, right? So the gradient here is always going to be 1, which means that as long as the value is positive, whatever gradient comes in like this, it just like gets multiplied by 1 and gets pushed out the other side. So it doesn't get harmed or squished or anything like that. So that's one reason why the ReLU is very popular, because it preserves the gradient while injecting almost like the minimum amount of nonlinearity to do interesting things. Yeah.
So by getting rid of those negative values, it has a little bit of nonlinearity to it to cause for it to bend,
features, dimensions, instead of
whatever.
just observations. Keep the same number of observations, but just take a small sample of the number of features that you're actually using.
Oh, I see. So you're saying, let's say you have 10 features. Instead of taking all data points of 10 features, what if you choose 5 features and just use them and do this thing, as long as you can actually compute the prediction. To compute the prediction, you may need all 10 features, right? Or you need to have some defaults for those features. And if you define defaults for those other 5 features, you're basically using all features. So that's the key thing. Can you actually calculate the prediction by manipulating? And typically you can't. All right? Okay, folks, 9:55, I'm done. Have a great rest of your week. I'll see you on Monday.
All right, you guys, that was awesome. That was a sweet lecture. I learned a lot there. I really solidified a lot of information that was a little bit more vague from our reading, right? So let's just kind of go through this really quick, right? So we talked about, we're going to use a case study. We're predicting heart disease here, right? We design a neural network taking in an input layer of 29 inputs corresponding to values on like a graph or whatever, or not on a graph, or a tabular data. Some of this data was flattened out via categorical data using one-hot encoding, right? These then 29 into 16 units with 16 more edges connecting to our output layer with 16 biases and one bias on our output layer, leaving to 479 total parameters in this neural network. It's just 4 simple lines of Keras code to set up this kind of model. And then we learned about, fitting loss functions to this model, right? So we talked about what is a loss function. It just quantifies errors of a model's prediction. And we learned about two of them today, a mean squared loss function, which is good for computing numerical outputs and like continuing values. And we learned about binary cross entropy, which is classification of 0 or 1, true false values. So it uses like a negative log function negative log function to do that kind of 0 or 1 all or nothing kind of feel for drastic changes towards 1 causes great readings towards 1 and vice versa. We then learned about the how to implement kind of this negative loss log model function into one of these loss functions overall, which is called binary cross entropy, which just uses the mean of all of those parameters, using that log loss function, and so then we can minimize these log loss functions, which is our goal here, by doing something called gradient descent, by taking partial derivatives of individual points with respect to all the other points held constant and computing a gradient descent along the negative gradient of the function to find local minimums. We then have the ability, right, this is going into the partial derivatives with respect to the other variables held constants for multivariable functions. Then we learned about backpropagation, which is just the way that you use gradient descent to update the weights of all of the parameters in the model. And there's certain calculus tricks that you can do rather than doing it iteratively one by one across every weight, thousands, billions, trillions of parameters in models, using some calculus tricks and things like that to compute backpropagation, layer by layer, referencing the layer the layer prior's computed values rather than doing recomputation from the start to the end for the whole thing. So I'm not super I need a little bit more solidification on backprop and seeing that in action, but this was a great lecture. Anywho, let me go ahead and sign it off here though for the time being. All right, you guys, let's go ahead and get back up to the front. Cool. All right, you guys, this was Hands-on Deep Learning 15773 from spring 2024 of MIT. Training Deep Neural Network Continued, Introduction to Keras TensorFlow, Application to Tabular Data. This was a super awesome lecture. You guys can find the notes in my GitHub link linked down below, as well as in the Discord where you can find a total roadmap. Thank you guys so much for being here. We'll continue on in the next one. Peace. All right, let me stop the recording. There. Nice. Yeah, that was a really good lecture. I am feeling a lot more confident on the flow of neural networks as a total, as well as into deep learning, transitioning or not, a little bit more application into the deep learning side of things. So hopefully my goal is I would like to implement a neural network from scratch in Python on our own once we get all the information we need. So we're kind of there. We can probably start to implement the beginnings of which, but I'm probably going to struggle with the backprop and the chain rule implementation at this part here. So maybe we'll just wait a few more lecture and maybe one more chapter, one more lecture before we give it a shot about doing our own, just to try to get some more exposure on this kind of back part here. But Discord is linked down below in the description. Appreciate you guys being here. Thank you guys so much. And I think I'm going to call it here. Just 2.5 hour lecture or 2.5 hour stream where we watched this lecture for today. I do need to continue on with our C learning. I do need to continue on. I'm having a lot of fun watching these lectures and learning. But we do need to apply the material into actual code and keep that going. We don't want to keep just learning and without actually applying the material. So we need to start doing some coding here pretty soon. So thank you guys so much for being here. This one is cool. All right, see you guys in the next one. I had a lot of fun. Thank you so much for 7,000 subscribers. We've gained over 2,000 subscribers in like a week, which is really crazy. I just keep checking it like every 3 or 4 hours, and it goes up another 300 or 400 subscribers. So it seems like everybody's really liking the deep learning content. So I did get a question though about why I'm watching this and not continuing on with the reading. I am doing the reading. I don't know why there's this like idea that once you do one thing, you're stuck to it and you can't use other materials to solidify the knowledge. Like there's no structure here, you guys. This is very just kind of spur of the moment, figure out trying to how we can do this and try to piece the puzzles together ourselves. So what we're doing though is we're using deep learning and with Python, a book, as our first exposure, reading over it, interpreting the words, the concepts in our own way. We're using YouTube videos and like small short form 3 blue 1 brown videos to solidify concepts visually. And then once we have a general understanding in our own way, we're coming in with a lecture to hit everything home and really drive the topics into our mind. So now I feel a lot more confident on neural networks, on being able to calculate the amount of parameters, being able to understand what's going on in the general flow. Just being able to hear it over and over and over again is key, Anyways, these are types of study strategies that I think what you guys should implement in your own. Anywho, I'll see you guys in the next one. Peace out.